I decided to turn my microphone down. I noticed on some of the YouTube recordings it was really loud, so I'm just a really loud guy. Okay, attendance grades are up to date. The solutions posted to homework 4, that's currently being graded. I actually didn't check it this morning. It might be graded. I need to check and see. No homework assigned today, because today I wanted to reserve our discussion totally for something I'm doing new this semester, which is the introduction of a project in this class, particularly a project related to something very near and dear to where we're at geographically, because we're going to be looking at designing or laying out and detailing a truss bridge very near to where we're at right now. It would help if I turn this on.
The ones from across the high river right
there? No. We're not doing anything that big, and you'll appreciate it when you look at the project constraints, because one of the project constraints is that no one member can be longer than, I think, 32 feet, and that would be a lot of members. That would be a lot of members. Let me talk to you a little bit about the goals. One thing I have not done is posted these notes yet to a Blackboard. I will, but I wanted to not do that because I wanted you to pay attention to what we're talking about today and just look at this. And I want to talk about my goals for this project so that I want you to understand where I'm at and my thought process with putting this together, and then we'll talk about the project specifics. And in order to make it easier for you, I'm actually going to walk you through an example set of calcs so you kind of get an idea of the scope, okay? So the goals of the analysis project, number one, I kind of wanted the project to be somewhat broad in scope in that you could lay out the truss that we're going to be talking about however you wanted. You can choose it and arrange it, and I don't think it'll be any more or less work depending upon how you choose to lay it out. So I wanted it to be that broad in scope that everybody could sort of do the project how they wanted, but I wanted it to be narrow enough in scope that you were clear in what you needed to produce at the end of the day. One of the things that always used to bug me when I was in college and I would have projects is I wouldn't really know what the professor wanted at the end of the day. And I want you to know what you need to produce at the end of the day. Okay? I want you to get a taste of design, a taste. This is a course in structural analysis. So because it's not a course in design, there's some details that we're skipping. And if you're interested in those details, take steel design. I'll tell you all about them. But I do want you to get a taste in design, particularly looking at both strength and service limit states. We'll talk about what I mean by that here in a little bit. I want you to get a flavor of taking what we're learning in here and combining it with different software packages. And so I can think of 3 software packages that you will combine probably for this exercise. One of them being Excel, one of them being some structural analysis software, and the third, and this is also my final goal, is I want you to force you to use some CAD again, because you're going to have to produce some drawings. So one drawing, only one drawing, and it's not even that difficult. I just want to force you to open one of those damn programs again, okay? It's a. I don't care. I don't care what you use. I don't care, because ultimately you're going to submit it as a PDF. I probably wouldn't even know which, so if it weren't for the little watermark on the PDF. Okay, so here's the goal. The goal is to design a pedestrian truss, or to lay out a pedestrian truss connecting this building to the adjacent biotech science center right next door. So here, like this door right here would be like right there, you know, right outside this door. And if you look at the elevations of the 3rd floors of both of these buildings, they were actually constructed so that the elevations would match. So if later on down the line we decided to do a pedestrian bridge connecting these 2 structures, much like this one here, that the elevations would work out. And so that's what you're going to be doing in your project, is laying out a pedestrian truss bridge in this fashion. So in order to do this, what you need from this course is the ability to analyze trusses and compute deflections. That's one of the reasons why I rearranged the course so that we did truss deflections a little earlier, so that that stuff would be simple. There are a couple of factoids that you need to understand in addition to what we've been talking about, and so I want to talk about that right now. Specifically, what you need to understand are, number one, this, as he put it, this confusing table in front of you, so that you understand what's going on with that. And two, you do need to understand a concept in structural engineering called tributary area. I will probably cover this more formally later on in the semester, but I need to give you a little bit of a taste so that you understand what's going on. By the way, your submittals for this project are not due until October and November, so this is not anything that's, due in the next few days. So let's start off with system loading and tributary area. The first thing I want to discuss are loads. So up until now, we've been doing structural analysis, and one of the things we really haven't talked about in detail are the loads, right? I give you a truss, and I say, here's the truss, and there's 50 kips on that joint, and 40 kips on that one, and 26 kips on that one, analyze it. But where did those values come from? Did they just miracle themselves out of existence, or did they come from somewhere? How do we determine the loads on a structure? If I'm designing this building, how do I design this floor beam? I need loads. I need force per foot. I need all of that stuff. Where does it come from? Well, it typically comes from what the structure is being used for. We have different loads that we apply to bridges than we do to buildings. We have different loads that we apply to simulate different types of load events, like dead load, like live load, like snow, like wind, like earthquakes. And a lot of times, those loads come from specifications, like the bridge spec, like ASCE 7, like what have you. We will talk about this stuff in a little more detail later, but the point I wanted to illustrate is that structural loads tend to be expressed, at least if we're talking about occupancy loads, like live loads and dead loads, etc., they tend to be expressed in terms of pounds per square foot. And they change with the type of structure that you're looking at. So for instance, if I'm looking at schools, I have different loads for the classrooms than I do for the hallways or for the first floor hallways. I have loads for offices, for dining rooms, balconies, etc. Whatever the structure is being used for, that changes the type of load that we apply. But if you look, you can see that those loads are expressed in pounds per square foot. When have we ever dealt with that in here? Have we ever dealt with a load that was a PSF? No, we have a truss and it's got 12 kips on the joint. 12 kips on the joint is not this, right? Okay, so that's different, okay? How do we handle that? Well, we handle that through the concept called tributary area. So let me give you the definition of what tributary area is and give you a couple of examples so that you can kind of relate what we're talking about. So tributary area is a definition that basically says if we're talking about a beam, a column, etc., the tributary area for that element is the loaded area that directly contributes to that member. And it's best defined as the area that's bound halfway to the next adjacent member. So let's take this room. See this right there? That's a column right behind this gentleman here. Okay? There's a column right here behind this guy that's on his phone. Boom. I got you. Okay, I'm just messing with you. All right, so here's a column, here's a column. Okay, I promise you that under this drop ceiling right here, between this drop ceiling and the next floor, that there are beams supporting this ceiling. So there's a beam running this way, and there's a beam, running this way. Okay, so let's take a look at this beam. I propose that this beam is responsible for all the floor area halfway over to the next beam. So it's responsible for everything over halfway here and halfway over to the next beam. So that would be this beam's tributary area, right? And then I would use that tributary area to say, okay, I've got a pressure load on this beam across this area. I can then take that, collapse that into distributed loads, point loads, to do my analysis. So here's a little bit more of a visual example. Here's a picture I took of the 3rd Avenue parking garage here at Marshall, right? So here's the garage. There's the basketball stadium. So here we've got these pre-top double T precast sections. And so the idea is that if I'm looking at, let's say, this beam, that this beam is responsible for basically like that floor area. Does that make sense? We would call this the tributary area for that member, okay? Now, one of the other things to keep in mind, and this doesn't really matter for the truss analysis, but I did want to kind of make this example. Structural engineering, when you're doing load takedowns, tend to follow a hip bone connected to the leg bone type of approach. The beams frame into the girders frame into the columns go down to the ground. So if you look, see these beams and see this, what I'm calling this girder right here, the girder looks a little bigger, right? Because the girder is responsible for all the load halfway over to the next adjacent girder. That's a bigger tributary area, right? So the girder is going to be bigger, right? That's, in a nutshell, kind of the idea, okay? So if we're looking at a floor plan, what we can do is look at a given element and we can say, okay, how is that element going to see that load? We can say if we're looking at a given beam, that this is its tributary area. Let's take a look at the beam. So let's say that's the beam and that's the beam's tributary area. Let's say that this, let's put some dimensions here. Let's make up some values. Let's say these floor beams are spaced, I don't know, 12 feet apart. That's kind of reasonable, right? How far is it from there to there? Maybe about that, right? Something like that. And let's say this floor above us is subjected to 40 PSF. I propose that if we're looking at an individual floor beam, what I want is to deal with this. I understand this. I can do structural analysis on this. I can do reactions, deflections, etc. How do I turn this into this? So let's take a look at this beam. What's that distributed load? I propose, let's look at this. Let's make up a value. Let's say this is 50 feet. What would be the tributary area of this beam if the beams are spaced 12 feet apart and the beams are 50 foot long? What's the tributary area? 600 square feet. So how much total load is the beam experiencing? If it's 40 pounds per square foot and the tributary area is 600 square feet, what's the total amount of load that the beam is experiencing? Well, you're on the right idea. So 40 pounds per square foot, tributary area, 600 feet squared. So what's the total load? 24,000 pounds, right? Now, to extend that a little further, and we aren't going to need to do this for trusses, but to extend that a little further, that's 24,000 pounds over a length of 50 feet. So what's that divided by 50? I propose that this 480 pounds per foot. Does that make sense? That's tributary area in a nutshell. That's all you need to understand. And trust me, I'll walk you through the math specifically for a given truss here in a bit. Does that idea make sense? Okay. That's the first idea I want you to understand. The second idea I want you to understand is this. I have in my hand a copy of the AISC Steel Construction Manual 15th edition. If you decide or elect to take CE 414, Structural Steel Design, there is no textbook for that class. This is the textbook. This is the AISC Steel Construction Manual. This is the document by which we design and detail steel structures in the United States. This is what you buy for the class. All the problems and whatnot are custom exams, so you don't have to buy a textbook. You just have to buy this, because you cannot do steel design without this. In fact, if you open up the FE reference manual, in the steel design section, they just snippeted pages out of this, because you can't do it without it. When we look at rolled shapes, hot rolled steel sections tend to be produced in two main fashions. We tend to produce plates or bars, like, half-inch thick plate, 3/4 inch thick plate, etc. or we produce rolled shapes like channels, angles. You're probably thinking of I-beams. We don't call them I-beams anymore because we have different types of I-beams, I-beams. What you're thinking of, what we would use in buildings, we call W shapes, okay? Now I'm curious if you have, thank you. I'm curious if you have experienced this yet in some of your other courses. If I describe this shape, a W10 by 49, do you know what these numbers mean? You know what the 10 means? Have you heard this yet? Okay. So if you have a shape that's a W10 by 49, the 10 is about how deep it is. Okay? If you look at this handout I gave you a handout, and if you notice that most of the shapes that are on this handout are W12s. Okay? And so, barring the ridiculously heavy ones, most of these depths are about 12 inches. They're not exact, but they're pretty close to 12 inches. Do you see that? Again, barring the super heavy ones. Now, here's another thing. I said barring the super heavy ones. How did I know which ones are heavy? This number is the pounds per foot. Okay? So, for example, and I have this on the next slide so that you have this. Oh, goodness. Oh, no, I don't. I left that slide out. I'll insert that and put that in the slide I put on Blackboard. But if you have a W10 by 49, the W indicates what type of shape it is. That would be like what you're thinking of as an I-beam. We call it W because it stands for wide flange shape. The 10 corresponds to the fact that it's about 10 inches deep, and the 49 corresponds to the fact of how much it weighs. So if I have a W10 by 49, it weighs 49 pounds per foot. Okay? Does that make sense? Now what you see here is a particular page out of the steel manual that details all of the W12 shapes. And there's oodles and oodles of properties. So for every row is a particular shape, okay? And if you look at, let's say, the W12 by 58, you'll see the area, the depth, the width of the flange, the thickness of the flange. On the page to the right, you'll see all the moments of inertia, the radius of gyration, all that stuff. I don't care about any of that. All I care about is the area. Why do I care about the area? We're about to do a truss analysis. And the deflection of a truss is found using the method of virtual work, and we do little f big FL over EA. All I care about is the areas. So you can ignore everything else other than those areas. Let me walk you through this process so that you kind of understand what we're going to do in this truss project. The big thing to keep in mind is when I go through this, software is your friend. Particularly Excel will be your friend in this project. And I'll show you why. Let's go through a truss layout. Now I'm giving you somewhat different parameters than what you're using in the project so that I'm not doing your project for you, but I want to walk you through it step by step. So let's lay out a truss for a 60-foot span. Your truss is not going to be 60 feet, so this answer is not going to work for your project, but you'll kind of get the idea. Let's lay out a truss for a 60-foot span. We'll say it's simply supported. Let's assume that the truss is 24 feet wide. Okay? So that means you got a truss here, you got a truss here, you're walking on down the bridge, and they're 24 feet apart. Okay? Now, let's assume that the bridge will need to support a load of 1,400 pounds per square foot. That's a lot. Okay? But we're going to assume that that counts for the pedestrian load. We're going to assume that accounts for the self-weight of the structure. We're going to assume that all the safety factors and all that stuff is built into it. So, again, it's kind of big, but we're going to assume all that stuff's taken into account. If you want to learn more about that, take me for steel design. I'll tell you all about it. For our bridge, we're going to employ the following limits. We're going to limit the member selection to W12s. So let's just talk practically. If you were designing a truss, why would you limit your designed to W12s? Like, why wouldn't you want W12s and then W18s? Well, the reason why is if they're all W12s, then they should all arguably be around the same depth, which makes it easier to connect one to the other, right? If you've got a member that's connecting to another member that's like this, what's the gusset plate look like? If they're all about the same depth, it makes the truss, the member-to-member gusset plate connections a lot easier to do. So it's common to limit the selection with stuff like this to a family of shapes. And because it's steel, we know that E is 29,000 KSI. Now, as you all are writing down these parameters, you're gonna, your pencils are gonna wear out pretty quick because I'm gonna show you a lot of results really quick. So just be aware of that. We're going to limit the stress on each member to 36 KSI. And I'm going to go ahead and tell you that if there's any one piece of this problem that's kind of a bunch of junk when it comes to real life, it's probably this. Because if you take steel design, one of the first things that you'll learn real quick is that the axial capacity of a member changes if the member's in tension versus the member's in compression. And we don't look at it from a stress standpoint. So there's a lot here, but because this is a course in structural analysis and not a course in steel design, and I just want to get you a taste of this process, I think this is okay for simplicity. The mid-span vertical deflection, we're going to limit it to 2 inches. I don't care what the truss looks like, I don't want it to deflect more than 2 inches. And finally, when it's all said and done, we're going to compute the cost of the truss, assuming steel weight or costs $1.40 per pound. It doesn't really matter what the unit price is, as you're going to see. Just need to pick something and go with it. I just kind of made that number up. All right. Everybody kind of get this concept? All right. Any questions? And again, if you miss something, I am posting these notes to Blackboard. Okay. So here's our step-by-step process. This is probably what I would write down. This is like the important stuff. The process is going to be as follows. The first part is going to be to use project constraints and guidelines to lay out the truss system. For this example, I'm just going to do it for you. But for your project, you're going to have to do this yourself. And I'm going to give you some guidance on how to do that later on. But we're going to use the project constraints and guidelines to lay out the truss. Then we're going to use tributary area to figure out the point loads on the truss. And we're going to analyze it. Once we analyze the truss, we're going to select the members based on the stress limits. And now that we have members selected, we can compute deflections. So we'll check the vertical deflection limit. Under the vertical deflection limits, we'll see if the truss passes. If not, we'll need to iterate the member selection, if necessary, and compute the cost of the individual truss. If there's anything that I would make sure that you understand, it's this. I'll give you a sec on this. This is probably like the most important part. Again, I'm going to show you a lot of data here real quick, and you're not going to be able to keep up with writing it, so don't worry about that. This is the important part. All right. With me so far, or you still need a bit? All right. You good? Okay. So what I'm going to do for this truss is I'm going to use a layout that looks something like this. Okay? This is going to be, we call this a Pratt truss. It's a very, very simple truss layout. The diagonals are all at a 1-to-1 slope ratio. I'm just keeping it very simple for the purposes of the discussion. If you remember, the truss is 60 foot long. So each of these panels are going to be 10 feet apart. And from here on out, I mean, the bridge itself is going to have 2 trusses. We're just going to focus on one of them, okay? So we're going to focus on this truss, okay? So this is my layout, okay? Now, what we got to do is we got to analyze this truss, means we got to determine loads on this truss, okay? So in order to determine loads on this truss, we're going to use the concept of a tributary area. So let's go back to the truss. So watch me on this. This is kind of important. Okay, so watch this. If we refer to the original truss, okay, the pressure load is 1,400 pounds per square foot, and the bridge width is 24 feet. Okay, so this dimension here is 24 feet. Okay, now each joint is 10 feet apart. Okay, so what I'm trying to do, let's just take this joint here. Let's see if we're trying to figure out how much load to apply to this joint. Well, what do I think is the tributary area for this joint? I propose that the tributary area is halfway over to the next joint, halfway over to the next joint, and halfway to the next truss. That is the tributary area. How would you compute that tributary area? Say it again. 10 by 12. Right? Half the width times 10 feet, 120 square feet. And so 120 square feet for a pressure load of 1,400 pounds per square foot is 168,000 pounds or 168 kips. Right? So what would happen, oh, there's my marker, is here's your truss, right? And I'm not going to draw all the members inside, but this is going to have 168, 168, 168, 168, 168, 168. What do you think the loads would theoretically be on the ends? Half that, right? But I'm going to ignore those because if I loaded the ends, look at the structure. Where are they going to go? They're not going to go to the truss. They're going to go to the supports, right? So I'm going to ignore those loads at the end, and you can do that for your truss as well, okay? So we're going to ignore the loads that go to the ends, and this would be our truss. Now that's something you can do, right? Everybody in here should be able to analyze this truss, right? So here's the truss. Determine your reactions. Boom, analyze it. Do I need to walk through that? You can do that, right? Like, yeah, I'm not saying we need to go through this step by step. You get it, right? You get the idea. Okay? Notice how one of the members is a zero force member. I'm going to talk about that here in a bit. Okay? In your truss layout, I would try and avoid those. Okay? And I'll explain why. But everybody with me so far? Now, I want to write down something. Okay? So that we're following along. I'm just going to pick a random member. Let's go with member HI. HI is experiencing a load of 672 kips. It doesn't really matter if it's compression or tension for what I'm about to do now, but let's just retain that for compression or tension. With me so far? Now, let's go back to your favorite course, Engineering 216. Remember this? Sigma equals P over A. So could I rearrange this to say A equals P over sigma? Could I do that? Now, let's see if anybody was paying attention. What's the sigma allowable for this problem going to be? 36 KSI. So somebody break out their calculator. If I took 672 kips and divided it by 36 KSI, what am I going to get? We'll say like 2 decimal places. 18.67 inches squared. You with me so far? So to select our truss members, remember we're limiting to W12s and we're limited to 36 KSI. I rearrange my sigma equals P over A expression. Take member HI, 672 kips, rearrange, and I get 18.67 square inches, right? Now, what is the smallest member that can safely resist that load? A W12 by 65. Does everybody see that? Go to your little handout that I gave you. Which member, which W12 has this area that's just a little bit bigger than that? Do you see that? See how the W12 by 58 has an area of 17 square inches? and the area of a W12 by 65 is 19.1. Do you see that? With me so far? So I propose, look at this truss here, okay? I propose that here's the truss, here's member W12 by 65, right? Okay? Now here's member W12 by 65, just do it for all of them. Boom, there's your truss. Remember how I said there was a zero force member? What do I do for the zero force member? I just pick the smallest one. The smallest one is the W12 by 14. With me so far? Okay. Now, what does this do for me? What this does for me is now every member has an area, right? And if every member has an area, I can now compute deflections, right? So, what do? I do this, right? Where is this truss going to deflect the most? It's going to deflect the most theoretically at midspan, right? So, put a load, a single unit load at midspan, compute the reactions, boom, do the analysis. Again, that should be easy, right? Okay, I've got little f's, I got big F's. What's my favorite tool as an engineer? Microsoft Excel, right? Take this, plug it into Microsoft Excel, boom, method of virtual work, okay? Method of virtual work, so the little f's, the big F's, the L's in inches, the E's, the A's, boom. I get a deflection of 2.2 inches. What's the problem? It's too much. That fails, right? That fails. Now what do? Well, unfortunately, the truss is deflecting too much. So what we need to do is we need to revise some of our member selections. I propose that a systematic and easy way to do this, again in Excel, is to focus on the members that have the largest amount of energy, all right? So what I'm going to do is start with like these members right here because they're the ones that are contributing the most to the deflection, right? And I'm going to up their sizes a little bit. So instead of a W12 by 72, I'll pick the next one. All I got to do is go into Excel, change the area, boom, right? Okay? And so the beauty of this is you can do this in Excel. So after I played around with it for a little bit, this is what I did. I ended up having to change a few members. I changed all the top chords and 2 of the bottom chords until I got the deflection to be less than 2 inches, right? Because I'm increasing the size of the members, I know that they're going to meet the stress limits. I'm not making any members smaller, I'm making them bigger. So now I have a truss that meets both strength limit states, i.e. the stress limits, and service limit states, the deflection limits. This is what I mean by system level design, that you're getting a taste. You have a truss and you got to meet 2 different sets of limits. You got a structure and you got to meet 2 limits. Not only the strength limit state, the limit on the stress, but the service limit state, that it doesn't deflect too much. So now here's my final truss. And what I did is I took the members that I changed and I made them blue. And if you compare those to the loads on the real truss, what you'll find is that those were the members that were experiencing the heaviest load. So it makes sense that we were bumping up those a little bit. And so now that I've got a truss, I only got to do 2 things. Draw it up in CAD and figure out how much the dang thing's going to cost. Remind me, for a W12 by 72, how heavy is that per foot? 72 pounds, right? 72 pounds per foot. And how long was this dimension? 10 feet. So that member weighs 720 pounds, right? 72 pounds per foot times 10 feet, 720 pounds. The beauty of Excel, okay? I don't know why I have these members highlighted. They're not supposed to be. I'll fix that because they're just supposed to be regular members. But here's the shapes. Here's the length. Weight times length gives you the weight per member. Don't forget to convert that back to feet. Add up all the weight. I get about 10,600 pounds. Steel costs $1.40 a pound. This truss is going to cost about $14,905. That's per truss. Remember, there's 2 trusses in the bridge, but I'm not worried about that. I mean, I just want to know how much a single truss costs. Does that make sense? Yes?
So we don't have to take into account for the other side?
No. I'm not worried about that. Because all it is, everybody's going to multiply it by 2. It's not going to say anything. You know, it's not going to reveal anything that's from an economic perspective. Yes, sir.
Can you use goal seek on the Excel to be able to figure out and change the area to make it?
Yes, and I got you something even better. Yes, I got you something even better because you'll like what I'm about to give you later on. Okay. Let me just show you what I'm talking about. One of the beauties of the steel industry is that they do a good job. They do a pretty good job in making stuff available for engineers. So one of the things that they do is they provide the shape database. Now, this is the shape database for all the shapes in the manual, and you don't need all that. What you need is this. These are all the W12s along with all their areas, and I'm going to post this in Excel on Blackboard so that you have that data. So, I mean, you've got this, but I'll post this to Blackboard too, but you'll have all the areas for all the shapes. It also does separate numerical columns for the weights, so you have that too. Like I said, I'll do you one like I told you, I'll do you one even better. And I'll show you a couple. I'll probably record a little video off to the side. I'll show you some commands called VLOOKUP. VLOOKUP will make your life a lot better. You'll love VLOOKUP. He's shaking his head because he's used VLOOKUP before. He's like, yes, you will. Make sense? All right, let's talk about now. What I did is I went through like a generic bridge. Let's talk about your bridge, okay? Here's the parameters for your bridge. So for your bridge, the span of the bridge will be 110 feet, okay? The pressure load is going to be a little less. It's going to be 900 pounds per square foot. Because the bridge is longer, I wanted to cut the load down a little bit because I didn't want the member sizes to get ridiculous, okay? Now, your bridge is going to be just like the one here in the sense that there's a truss on either side of the bridge. Like there's a truss over here and a truss over here. And you really just need to worry about detail in one of them because they're both going to be the same. For your bridge, you are to employ the following limits. You are going to limit your member selection, again, to W12s, okay? The axial stress on each member will be limited to 36 KSI. Now, for the deflection, I'm expressing the deflection a little differently. I'm saying that the mid-span vertical deflection of the truss is limited to what I'm calling L over 360. Typically, this is how deflection limits are expressed. You don't tell people that the deflection is limited to 2 inches. You express it as a fraction of the span. So the idea is that if a bridge is 100 foot long, it can deflect more than a bridge that's 20 foot long, right? Because it's the length divided by some ratio. We're going to also, for the dollar value, we'll take the same unit cost. We'll say $1.40 a pound. The next slide also has some juicy stuff, so I'll give you a minute on this.
Is $1.40 a pound close to what it actually is?
I don't think it is this year.
So it's complicated, and here's why it's complicated. Number one, as he said, prices fluctuate. Number two, it varies from state to state in terms of sourcing, in terms of time of year. There's also no labor, no overhead, no permitting, none of that. So, no, but I'm keeping it simplistic. Let me say this. What I'm focusing this project on is mainly the structural analysis components. If this was a construction estimating course or capstone, we do a lot more on that side, and you get a whole heck of a lot more detailed on labor, and we talk about overhead and all of that. So I just want you to get a flavor for it. So now, this is important, so you might want to watch, and then I'll leave it up to where you can see the whole thing, but I really want you to pay attention to this slide. One of the things that I didn't do in this example is I said the first step is to lay out the truss according to project constraints, but I didn't tell you what those project constraints were. I just said, here's the truss. You're going to have to come up with the truss. So here are your constraints, okay? Number one, for your truss layout, IT has to be 0, okay? So I want a stable and statically determinate truss. There is a reason for that, okay? The main reason is that if your truss is determinate, then you can change the members and it doesn't change the analysis results. That is to make it easier on you. If the truss is indeterminate, every time you change a member, it changes your big F's and little f's. I don't want that to happen. So you need to lay out a truss where IT is 0. The truss will be simply supported at the ends, so by default, IE will be 0. So just like the truss that we had here, there's a hinge support over here and a roller support over there. Third, vertical deflection will be measured at the lowest joint at midspan. So however you lay out your truss, you need to have a joint at midspan at the bottom of the truss, okay? You can't lay out your truss to where, I don't know, like, I'll do a really, really short truss, but you can't do this. You can't have like a support, here's the truss, and it can't go, you know, like this. This would not be good because then you wouldn't have a joint at midspan. Okay, you need a joint at midspan in order to determine deflections. Okay? No individual truss member may be longer than 32 feet. Okay? And finally, the truss must not exceed an envelope plus or minus 18 feet from the walkway. So what that means is, like, if here's your walkway, right? Here's where the people, you know, will walk, right? You can have an overhead truss or you can have an overhead truss. I'm fine with either one, right? But the overall depth of the truss can't be more than 18 feet, okay? That's your limits on how you lay it out. If I need to pose. Thank you. I'm such a dork, I know. So I'm calling those through trusses and deck trusses. Deck trusses would mean you walk on top of the truss. Through truss would mean you walk on the bottom. So there's two trusses. There's two bridges. The one that's furthest isn't behaving so much like a truss overall, but that one's a through truss. That one right there. So I put a picture in it. At least, hold on. Yeah, it's in the slides. I don't, because of all the animations, I don't want to go back. So. And I got some details coming up here in a bit on the deliverables. And again, I'll post some more info on Blackboard so that you're aware. I won't leave you in the dark.
I'm glad you didn't do this on that one Friday.
What Friday?
That one that we didn't have class.
Oh, I wouldn't have done, no. I thought about it, but then I would have been rushing deflections. I don't think that's right, you know. I wanted to give deflections their time. Can you imagine if we did all the deflections in one day? That'd be pretty rough, yeah. All right. Submission number 1. There's 2 submissions for this project. Submission number 1 is due Wednesday, October 13th. This is a very, very, very simple submission. What I want you to do is I want you to come up with 3 truss evaluations, or 3 truss elevations. Sorry, not evaluations, elevations. So 3 truss layouts, 3 separate ones. And these can be hand-drawn or done in CAD. I just want you to sketch it out. No analysis. I just want you to come up with the overall layout, okay? Verify for each truss that IT is 0, okay? And then I want you to develop a selection strategy. And what I mean by a selection strategy, there's no real wrong answer. You could say, I'm picking this truss because it has the fewest number of members. I'm picking this truss because it's deepest. I'm picking this truss because I did some research and it told me it was an effective type of truss for bridges. Whatever, I don't really care, but I want you to document why you picked one truss over another, okay? So you're going to come up with 3 truss elevations and choose one and tell me how you chose it, okay? You can draw these hand-drawn neatly, so no rough sketches. If you're going to do it by hand, use straight edges, etc. And I want you to submit a single PDF, okay? All I want, it doesn't, I mean, you can do it as like some big old formal report. I honestly don't care. You could format it like a homework assignment. I'm okay with that. But I need a sketch of each of the associated truss layouts along with their associated IT computations. And I need a small write-up, maybe like a paragraph, explaining how you chose one concept. That's what I need. That's submission 1, okay? With me so far? Okay. Submission 2, because we're running short on time, is due the Friday before Thanksgiving break. Here's what I want in that submission. I want you to select the truss members to meet both stress and deflection limits. I want you to tell me the cost of an individual truss. Basically what we did today. For this submission, you're going to submit 3 things, and so you'll be able to upload 3 items to Blackboard, okay? You need a CAD drawing of your final truss. You need a set of these computations, and you can do those in Excel. I'm fine with that as long as it's neatly formatted, or you can do it by hand. I recommend that you do it in Excel. And a set of results from structural analysis software, and there'll be more on that later because we haven't covered it yet. We will, don't worry. Finally, my tips and tricks for you. Number 1, truss symmetry is your friend. Laying out a symmetric truss means you only have to analyze half of it, right? I think makes sense. If truss symmetry is your friend, Microsoft Excel is your best friend. You can do a lot of these calculations in Excel and make your life a lot easier. Avoid zero force members in the real structure if possible, because all that's going to do is add cost. I do want you to try and optimize your design to get the lowest cost, which during submission 2, if you need to tweak a joint location here and there, that's fine. And I'm going to talk about the last point in a bit. Use the IT expression to help determine your geometry. So if you know your truss is going to have, let's say, 15 joints, you can determine how many members it should have. And you can do that to check to make sure the geometry makes sense. But finally, don't be afraid to get creative with your truss layout. We are going to have some structural analysis software that's going to make the grunt work a lot easier for us, okay? So don't be afraid to get creative, okay? That's okay. Like if, this truss that I did was really boring. Maybe I could have given it some curvature, made the truss a little bit more, with different slope ratios. Maybe I could have used a deck truss. It's okay. Don't be afraid to get creative, because I truly do not think that getting a little creative with your geometry is going to cause any more work, given the fact that you're going to have some software to make your life a little easier on the analysis side. So it's really just what you want to do. Have fun with it, And if you get creative, I guarantee you can probably reduce the cost of that truss. Like the truss that I showed you, I could do better. I could do better by changing the geometry a little bit. Trying to get around that zero force member. That's just a waste. I could do better. I know you could too. Any questions? That's your project. Does that make sense? Clear in scope, hopefully. And hopefully not a terrible amount of work. I don't want it to be like nights and nights of work. I want it to be pretty straightforward. Sound good? We start shear and moment diagrams on Wednesday. That's all I got. We'll see you.